Okay, so it seems like there's been a few issues with 7.4, kind of in general. So there's already a video in Moodle on just solving linear inequalities in two variables. So basically what we do is we graph those. So what I want to do in this video is I want to kind of remind you how we graph linear inequalities in one variable, how we graph a linear equation in two variables, and how that leads us to graphing a linear inequality in two variables. But the big focus of this video is going to be systems of linear inequalities in two variables. Okay, so with all of that said, let's go to the whiteboard. All right, so let us begin. Whoops, sorry. Okay, so again, we're really technically talking about systems of linear inequalities. But first, that's supposed to be a first. I can hear my neighbors outside talking and it's very distracting. But first, there's some stuff that we have to remind ourselves of. So first of all, let's go way back to 6.4, okay? Back in 6.4, we talked about linear inequalities in one variable. So we would have solved a linear inequality and we could have gotten something like this. X is less than 2. So what that looks like graphically is you have a number line. We have a boundary point of 2. So we locate that on our number line. And then we have to decide which half of this number line we want to shade. Are we going to shade the left half or are we going to shade the right half? And it all comes down to the inequality symbol. In this case, we know that X values have to be less than 2. So we ended up shading to the left here. And then we always had to determine, well, what do we do at exactly 2, that boundary point? And the inequality symbol tells us what we do. For a strict inequality, less than or greater than, we would put a circle here, but we would leave it nice and open. That basically told the reader that, hey, everything less than 2 is good, but exactly 2 cannot be included. You could also have something like X is greater than or equal to -5. So again, we would draw a number line, we would locate the boundary point, and then we would determine which half of the number line we shade. Would we shade the left half or the right half? Well, this one says X values have to be greater than -5. So I would shade everything to the right because values to the right of -5 are bigger. But then again, we always had to come back and ask ourselves, what do we do at exactly -5? Well, we can include -5. -5 is part of the solution. So the way we tell our reader that was we would put a circle there, but we would fill it in. So this says the solution is -5 and anything bigger than that. So that was way back in 6.4. So then if we go back to 7.2, we had situations where we were solving linear equations in two variables. And really what that meant is we were graphing them. So we could have something like y equals 2/3 x minus 5. So what I told you back then was you would take this right here, this equation, it is in slope intercept form. And what you would do is you would determine the slope. The slope, if you're solved for y, is always the coefficient of x. You would then take the y-intercept, which again, if you're solved for y, the y-intercept is -5. And then what we would do is we would graph that on a Cartesian plane. So here's how that works. All right, so what you do is you plot your y-intercept. Well, our y-intercept occurs at -5. So the vertical axis, that's the y-axis. And we want to go down 1, 2, 3, 4, 5. Okay, so that's our y-intercept. That's where our line is going to cross the y-axis. From there, we would then apply our slope, and our slope is positive 2/3. So this would tell us to go up. So we go up 2, and then we would go to the right 3. And then from there, we could just connect the two lines. Pretend I actually connected here. I missed it a little bit. We would connect the two lines with a line and arrows, and that was the solution to y equals 2/3 x minus 5. Now remember, the solutions to a linear equation in two variables, it's all of the ordered pairs that satisfy the equation. Graphically, what that is it's all the ordered pairs that make up the actual line, okay? So then we need to go back to the first half of 7.4, okay? So again, I already have a video in Moodle on how to graph linear inequalities in two variables, so I don't want to redo a whole video, but I do want to at least remind you how to do it because it's going to fall into place. Hopefully it all falls into place in time for us to cover systems of linear inequalities, okay? So we would have had something like 2x minus 4y was greater than or equal. Let me actually just do greater than 8, okay? So what we would do here is we would solve this inequality for y. So in order to solve this for y, I would start by subtracting 2x. That gives me negative 4y is greater than negative 2x plus 8. All right. And then you would divide each term by negative 4. And you have to remember something that's very, very important. When you multiply or divide an entire inequality by a negative, it reverses the direction of the inequality symbol. That's going to happen here. So when we divide all of the different terms by negative 4, for the first term, the negative 4's cancel. Negative 4 divided by 4. Negative 4 divided by negative 4 is positive y. And then we reverse the direction of the inequality symbol. And then negative 2 divided by negative 4 simplifies to be 1/2 x. And then positive 8 divided by 4 is negative 2. So this is what we're going to focus on right here, okay? Now, we need to think about 4 really important pieces of information. The first, what is our slope? Well, our slope is positive 1/2. The second thing we have to look at is what is our y-intercept? Well, as long as you solve for y, remember the slope and y-intercept, you get them for free. The slope is always the coefficient of x, and then the y-intercept is always the constant. So our y-intercept is negative 2. And then remember, we had to find a way to make the two worlds from 6.4 and 7.2 collide. And so we have to realize that now with this, we're talking half planes instead of the left side on the number line or the right side on the number line. We also have to realize that the actual line itself is the boundary point. So instead of having a single boundary point like we have over here on the far left, you're going to have a boundary line, and you either include the points on the line or not. So in this case, we have a strict inequality. So that would be like over here where we had x is less than 2 and we did not include the exact value 2. Well, that's what's happening for this last example on the right. We cannot include the ordered pairs on the line. And the way we explain that or show that to our reader is we graph the line, but we use a dotted line instead of a solid line. That tells the reader that the ordered pairs on the line don't count. They're not part of the solution set. The last thing you have to do is you have to shade a particular half plane, okay? So when you solve for y, this right here kind of tells you which half plane you're gonna end up shading. So if you have y is less than, that tells you that you're gonna shade below. However, and this was something we talked about a good bit in class, but what shade below means is you literally shade the half plane that's underneath the line. Okay, but we still have to test a point just to really verify this, okay? So anyway, that's what we're going to graph right here. We're going to graph the inequality y is less than 1/2 x. Our slope is 1/2. Oh, wait a minute. Y is less than 1/2 x minus 2. I forgot the minus 2. Our slope is 1/2. Our y-intercept is negative 2. We're going to connect the points with a dotted line, which tell us that we cannot include the ordered pairs on the line in our solution. And then we're going to shade below. But let's go ahead and start graphing, and then we'll talk more about what all of that means. All right, 1, 2, 3, 4, 5, 6, 7, 8. Sorry, I do have my door open at home, and it is a little bit noisy, but I think you should be able to still hear me. All right, so I want to start by plotting the y-intercept. The y-intercept is -2. And then from the y-intercept, the slope tells me I can go up 1 to the right 2. So I'm going to go up 1 to the right 2, up 1 to the right 2. I could also go down 1, but if I go down 1, I would need to go to the left 2. All right, so I have several points on the line right now. I want to stop, take a breath. Our gut instinct is always to connect these points with a solid line, but in this case, we want a dotted line. So we're going to do a dashed line. And then this red dashed line, what it does is it splits the Cartesian plane into 2 regions. Those 2 regions are the half plane, okay? So above the red line is the half plane that would be greater than, and then below the red line is the half plane that would be less than. So what's interesting here is when you go back to the far left-hand side of this screen, we have go way back to 6.4. We either shaded the left or the right side of the number line. Here on the far right, we're not shading the left or the right, we're shading the half plane that is above the line or the half plane that is below the line, okay? So here's how we know what to shade. We test a point. You want to test any point, does not matter what point. You just want it to not be any point on the line. So we're going to test the origin. I test the origin just because it's easy to plug in zeros. So we can see that the origin is above the line, okay? We're going to test 0, 0, and the way we test it is we plug it back into the original inequality. So I would get 2 times x, which is 0, minus 4 times y, which is 0, and we want to know if that is more than 8. Well, 2 times 0 is 0, 4 times 0 is 0, and 0 minus 0 is 0. So is 0 less than 8? No, this is false. 0, or is 0 greater than 8 rather, and no, it's false. 0 is less than 8. So what that tells us is that the ordered pair 0, 0 is not part of the solution set. And because it's not part of the solution set, everything above the line is also not part of the solution set. So that tells me that I definitely want to shade below the line. Let me actually do that in red. So I want to shade this below the line, and this is my solution. So the solution to this linear inequality is every single ordered pair below the line, but not the ordered pairs on the line, okay? So what needs to happen now is we're going to take all 3 of these ideas, so really especially this stuff from the first part of 7.4, and we want to apply it to what we know about systems of equations, okay? So remember, systems of equations, we have 2 equations that we're solving simultaneously, and what we were looking for was the point of intersection. So recall systems of equations, systems of linear equations are 2 equations that we solve simultaneously, that we solve simultaneously. The solution to the system is the point where the 2 graphs intersect. So we're just going to sketch something here. So let's say we have one line that does this. Let's say we have another line that does that. What we're looking for is this point right here. This is the solution. So we have to take this idea along with this situation from the first half of 7.4 where we're solving a linear inequality in 2 variables where we have to graph it and shade a half plane. We need to take those 2 ideas and combine them to get systems of linear inequalities. So here's the deal. A system of linear inequalities is 2 linear inequalities. Whoops. that we solve simultaneously. The solution, it's no longer a single point where the two lines intersect. Instead, the solution is the set of all ordered pairs that satisfy both inequalities. So what that means is this solution. So the solution is where the shaded regions overlap. So let me draw you a picture. So again, this is equations versus inequalities. So let's draw a picture of what this really means. So let's say we have some line that does maybe this, and we have another line that does this. And let's say we want to shade the half plane above the blue line and the half plane below the red line. Well, what that would do is it would give us this. This is where the shaded regions would overlap, okay? So you would have this right here. All right, so the shaded region again would be all of this. I'm going to color it in really dark so you can see it. So that would be the actual solution to this system. Okay, you would want everything where the red and blue shading overlap. Okay, so everything right here is not in the solution set. Everything right here is not in the solution set. Everything right here is not in the solution set. The solution is only the two where the two shaded regions overlap. Okay, so now let's go ahead and try this with a couple of examples. Okay, so let's look at how about this one? We'll do a really easy one to start. So y equals negative 2x plus 4. Don't put equals, bless my heart. We want y is less than 2x, negative 2x minus 4. And then we want y is less than or equal to x minus 4. All right, so you do want to graph both of these inequalities on the same Cartesian plane. Whoops. So I am going to graph them in different colors, so it's hopefully a little bit easier to see. All right, so for the first inequality, we're going to graph it in red. So for the first inequality, the slope is, remember, the coefficient of x. So I'm going to write it as negative 2 over 1 because I do want it to be a fraction. The y-intercept is the constant. Again, this is only true if you've solved the inequality for y. So for the first equation or the first inequality, the y-intercept is 4. Now for the first inequality, we have y is less than, not y is less than or equal to, strictly less than. So we do want to connect the points here with a dotted line. This just means, because we have strictly less than, this means the points on the line cannot be part of the solution set. And then finally, we think we're going to shade below. So remember, if you solve for y, the y and the inequality tell us which direction we're going to shade. We think we're going to shade below the red line, but we'll double check with a test point. Okay, now for the blue line, we have the slope is 1. So I'm going to write that as 1 over 1 because I need it to be in fraction form. Remember, the coefficient of x, if you have solved for y, is the slope. The y-intercept, if you have solved for y, is just going to be the constant. So it's negative 4. Now here we have y is less than or equal to. That or equals to tells us that we can include the points on the line. And the way we tell our reader this is we connect the points with a solid line. And then finally, we have y is less than or equal to x minus 4. That less than or equal tells us that we're going to shade below. But again, we're going to test a point just to make sure. All right, so let's look at the red line. Actually, let's finish our Cartesian plane. Now remember, if I freehand this, it's going to be a little wobbly, so use your imagination, pretend it's perfect. Okay, so for the red line, we have a y-intercept of 4. So we're going to go up to positive 4 on the y-axis. And then from there, we're going to apply the slope. So the slope tells me I can go down 2 to the right 1. So I would go down 2 to the right 1. I could go down 2 more to the right 1. Instead of going down and right, you could also go up 2, but if you go up 2, you have to go to the left 1. All right. Either way, get 3 or 4 points on there and then pretend they're perfectly straight. Don't forget that's super important when you freehand. This one I can already tell is going to be a little wobbly. But we do want to plot these points with a dotted line. And we'll worry about the shading in just a minute. I want to get both lines on the Cartesian plane and then we'll talk shading. Okay, so let's look at the blue line. Now the blue line has a y-intercept of -4. So I'm going to go down 4 on the y-axis. The slope is positive 1. So that tells me to go up 1 to the right 1. So I'm going to go up 1 over 1, up 1 over 1, up 1 over 1. I could also go down 1, but then I would have to go to the left. All right. So these points need to be connected with a solid line because remember, we can include the points on the blue line. All right. So we've got our system almost graphed. What we need to do now is talk about the shading. So we're going to test 2 points. So for the red line, I'm going to test a point. And then for the blue line, I'm going to test a point. You can test the same point. You can test different points. It does not matter. Just test a point for each. Okay. Let's say we test the origin for both, okay? The reason I choose the origin is only because it's easy to plug in zeros, okay? So I'm going to test 0, 0. So I'm going to plug in 0 for x and y into that first inequality. So y is 0. We want to see if that is less than -2 times 0 plus 4. Well, -2 times 0 is, let's see, where am I at? -2 times 0 is 0. And then plus 4. So 0 plus 4 is 4. Is 0 less than 4? Yes, this is true. So what this tells me is that 0, 0 is part of the solution set. So I would want to shade everything below this line. So like everything like this. And I'm just going to gently shade it for now. Okay. Now for the blue line, let's again test 0, 0 just because it's super duper easy to plug in zeros. So I've got y is less than or equal to x minus 4. So y is 0. We want to see if that's less than or equal to 0 minus 4. All right, so we have 0 is less than or equal to -4. Is that true? Well, it just so happens that 0 is actually bigger than -4. So no, this is not true. It's false. All right. So basically what's happening here is this point is part of the solution for the red line. This is not part of the solution for the blue line. And so right here, let me just point out really clearly, this is the origin right here. So we can see for the red line, it is below the red line. So that tells me the origin is part of the red shading, but it is actually above the blue line. And we verified that with this test point. The test point didn't work. All right, so that tells us we're going to shade below the blue line. So then we want to look at where the shading overlaps. And it is all of this right here. All right. So what I'll tell you about inequalities is they're messy. So like when you have a system of inequalities, it's like having 2 linear inequalities that you're graphing at the same time. It just gets kind of cluttered. It just gets kind of messy. I would encourage you to use different colored pens or markers or something when you graph these. If not, just be really, really light when you do your shading. And then once you figure out where the shading overlaps, color that in a little bit darker. All right. So that's one example. Let's look at another example of this, and then we'll look at horizontal and vertical lines too. So let's say that we have, let's do x plus 2y is greater than 4. And then 2x minus 3y is less than or equal to -6. Okay. So first thing I want to do is I want to put both of these equations in slope intercept form. Okay. So for the first equation, I have x plus 2y is greater than 4. I want to solve for y. So I'm going to subtract x. That's going to leave me 2y is greater than negative x plus 4. All right. I then want to divide all parts by 2 because we're trying to get the y alone. Well, on the y term, 2 divided by 2 is 1. 1 times y is y. On the x term, everything simplifies to where we would get negative 1/2 x. And then for the constant, 4 divided by 2 is 2. So let's do everything for the first equation. We're going to do it in red. So the slope for the first inequality is the coefficient of x after you have solved for y. So negative 1/2. After you solve for y, the constant is the y-intercept. So the y-intercept here is 2. We have a strict inequality. We're just strictly greater than this line. So that means the points on the line cannot be part of the solution set. So we're going to connect the points with a dotted line. And then we have y is greater than. So that tells us the solution is bigger than this line. So that tells us to shade above, but we will again test a point. All right, for the second equation, we have 2x minus 3y is less than or equal to negative 6. Again, we're solving for y, so I'm going to start by subtracting 2x. That's going to leave me with negative 3y is less than or equal to negative 2x minus 6. Let me get a sip. I'm getting dried out here. Okay, so now in order to finally get y alone, we divide all 3 parts of this inequality by negative 3. And you have to remember, if you multiply or divide an entire inequality by a negative, you have to reverse your inequality symbol. So as we simplify, we also have to reverse the inequality. So for the first term, negative 3 divided by negative 3 is 1. 1 times y is y. We flip the inequality symbol. It now becomes greater than or equal. And then for the x term, negative 2 and negative 3 simplify to be positive 2/3 x. And then finally, negative 6 divided by negative 3 is plus 2. So let's do everything for this equation or this inequality in blue. So once you solve for y, the coefficient of x is the slope. So our slope is 2/3. Once you solve for y, the constant is the y-intercept. So the y-intercept here is 2. We do not have a strict inequality. This inequality is greater than or equal to. So that tells us that the points on the line can be included in the solution. So that tells us that we're going to connect the 2 points with a solid line. And then finally, we have y is greater than or equal to. So that tells us that all of the ordered pairs above the line are going to be part of the solution. So again, we would shade above. But for both examples here, we're going to test a point. Okay. Whoops, I think I said below. I'm in above. All right, so let's get to graphing. I'm telling you, the traffic beside my house today is insane. I can't tell if you all can hear it or not. All right, so red line first, we're going to plot our y-intercept, which is 2. Our slope is negative 1/2. That's going to tell me to go down and to the right. So I'm going to go down 1, to the right 2, down 1, to the right 2. I could also, instead of going down, I could go up. But if I go up, I have to go to the left 2. Now, these points, we want to connect with a dotted line. All right, and just like the previous example, let's hold off on shading until we're done putting both lines in here. So let's look at the blue line. So for the blue line, the y-intercept is also 2, but this time my slope is 2/3. That tells me to go up and to the right. So I'm going to go up 2, to the right 3. I could, instead of going up, I could go down, but if I go down 2, I go to the left 3. Now for these points, we connect them with a solid line. Kind of missed a point. All right, so now let's figure out the shading. So for the red line, let's go ahead and just test the origin again. The only reason I test the origin is just because it's easy to plug in zeros. So for the red line, I'm going to test 0, 0. And I'm going to plug it into that first original equation. So x is 0. Whoa, that got out of control. So x is 0. And then y is 0, so I get 0 plus 2 times 0, and we want to know if that is greater than 4. Well, 2 times 0 is 0, so I get 0 plus 0. 0 plus 0 is 0. Is 0 greater than 4? No, this is false. So that tells me the origin, which the origin, in case you're unclear, is down here. That tells me the origin is not part of the shaded region. So for the red line, below the red line, we cannot shade that. That verifies that we would shade above. So I'm just going to very gently do some swipes above so you can kind of see where the red shading is. Now let's look at the blue. So again, I'm going to test the origin simply because it's easy to plug in zeros. So for the second equation, we have 2x minus 3y is less than or equal to -6. Anywhere I see an x, I'm going to plug in a 0. Anywhere I see a y, I'm also going to plug in a 0. So 2 times 0 is 0. 3 times 0 is 0. 0 minus 0 is 0. So then the question here is 0 less than or equal to -6? No, this is also false. Okay, so this tells me the origin, which is below the blue line, cannot be part of the solution. So none of the points below the blue line can be part of the solution. So that verifies that we do shade above the blue line. So now that you've seen this very light shading, you have to figure out where the actual solution is. Remember, the solution is where the overlapped regions, where the two shaded regions overlap. So this right here, I'm going to just darken it in really nicely. This is your solution. Any point that falls into this shaded region is part of your solution, including the points right here on the blue line. However, the points here on the red line, they do not count. They're not part of the solution set. All right. So the last example I want to cover is horizontal and vertical. So they're actually quite a bit easier. So let's say we have a system of inequalities and it is x is less than 3, y is greater than or equal to -1. So here's the deal. For x is less than 3, this is vertical. Actually, I can just do this right here. So this is vertical, and I think I might do the vertical line in red. Yeah, let's do this. This is a vertical line through 3, 0. So since we have x is less than 3, 3 is the actual x-intercept. We'll do the horizontal line in blue. And this is a horizontal line through 0, -1. And remember, we know that these are horizontal and vertical because if you don't have two variables in your inequality, that means you can't touch both axes. And if you don't touch both axes, you're either horizontal or vertical. So for x is less than 3, we have an x, which means we have to touch the x-axis, but we do not have a y, which means we cannot touch the y-axis. So that tells me I have to be vertical. And I am going to do the vertical line as a dotted line because it is strictly x is less than. So that means the actual points on the line don't count. And then for the horizontal line, we have y is greater than or equal to. So I want to go ahead and do this line as a solid line because the points on the line do count. And now we have to figure out our shading. Okay, we want to be above the blue line because we are greater than. But for the red line, we either have to be to the left or to the right. And since this is x is less than, we want to be to the left of the red line. So again, we want to be above the blue line. We want to be to the left of the red line. So our solution is where all of this shading overlaps. So our solution is here. All right. So that's pretty much it. That's systems of linear inequalities. They're not the hardest thing you're ever going to see, but they're a little messy. They're a little tedious. We're also in this, let me see here. Whoops. So when we're dealing with inequalities, we're also assuming you know a lot of stuff. So that's kind of how I started this video. We're assuming you already know how to graph linear inequalities in one variable. And you should, because we did it back in 6.4. We're also assuming you know how to graph linear equations in 2 variables. You should, we did that in 7.2. We're also assuming that you understand how to graph linear inequalities in 2 variables. And at this point, you should, we did that at the first part of 7.4. So then we take all of that information and we kind of like put it together, and that gives us how to solve this. And you also have to understand systems of inequalities, that's 7.3. But we take all of that together, and that helps us understand how to graph systems of linear inequalities in 2 variables. Okay, so again, the traffic beside my house, I'm sorry. So it seems like attendance has been pretty rough this past week. So that's why I made these 2 videos. I will not always make videos, okay? Because I am not here to recreate what I already did in class. But it just seems like this stuff, the people that were in class struggled with it. And then a lot of people missed it, okay? So that's why I made these videos. So keep in mind, this is not always gonna happen, all right? Hopefully these helped. If not, go to the book, all right? Good luck.